Hello and welcome to the last session for our discussion on growth and decay models. Just before we start, I apologize in advance if you hear some background noise. There's some construction happening upstairs that I cannot control. So, we are talking about the logistic model. Now we did one example, maybe one isn't really enough to really get a good grasp of what's happening here. So I thought let's add on a part two to just be sure about what is happening. So let's recall one way to look at this is our basic exponential model says that the growth rate is proportional to the population size at that time. The per capita growth rate is the growth rate per person for the exponential model that is constant, which isn't really super realistic because it says that even if you have a ton of people, the growth rate is the same, yet with that many people, space becomes an issue and it actually throttles the growth rate back. So our logistic model, one way of looking at it is to say that let's step up the per capita growth rate one step more general and make it linear. So we could call this now linear in y. So m slope y plus b. Think of your y equals mx plus b, but now y is the variable in that linear function for the right-hand side. So, of course, we're going to make m here negative so that the higher the population, the lower the per capita growth rate. Okay. So then when we multiply y on both sides, we get our differential equation in its more familiar form, y times my plus b. And now you can rewrite that and get a growth constant and whatever by factoring out the m and so on. But this is another way of understanding how the logistic model generalizes the basic exponential model. Now our other version, I'll say, our other view, let's say here, our other view is to say that the basic exponential model was the growth rate proportional to the population size. Our capacity model was saying that the growth rate is proportional to the difference, the distance from the capacity. If I put these together, the growth rate is proportional to this one, proportional to that one, so proportional to both, perhaps a different proportionality constant, perhaps not. I just use a k regardless, and we get our logistic model. Now these two are the same, it's just a different view to arrive at the same differential equation. Now we started with the bottom one yesterday. I'm going to leave this one up. So here we have our capacity, and I can rewrite this top one to make it look like that once I have the M and the B maybe. So that might be simpler if we look at a specific example. So let's perhaps do that, and it might be a little nicer to look at actual numbers. So I have an example here just taken from a random textbook. Now I'll just say I'm not going to use a B because the D and the B, they look a little too similar. I'll stick to my Y. So whenever you see the function name, we're just going to use the function name Y. It's more familiar, it's more comfortable, just so you know. So our B will be called Y. That's our function, our population function. There's also one typo in here that I'll get to when we get to that word. Suppose that our function measures the number of bacteria living in a colony in a petri dish, where our function is going to be Y, is measured in thousands, time is measured in days. One day you measure, or one time you measure that there are 6,000 bacteria and the per capita growth is 3. Now here's the typo. This should actually be hours. A few hours later, you measure that there are 9,000 bacteria and the per capita growth is 2. Assume the per capita growth rate is a linear function, which is what the logistic model assumes. Generalization from the basic exponential model. Use the measurements that they gave me to find this function and write a logistic equation, the differential equation. Okay, so let's do that. Just get rid of this here. So we have our example. So we're just going to let Y represent the population size of the bacteria population at time t, and it's okay if t is in days. That's not a problem. So now what do we know? We're given that at some time, it doesn't really matter when, we have y equal to 6,000 and dy dt over y, the per capita growth rate is 3. Then at some other time, we have y equal to, I believe it was 9,000, and the per capita growth rate dy dt over y equals 2. Let me just see if I am set up here correctly. All right, all good. All good. Get MathBot ready for eventual calculations. Okay. Now, for the logistic model, our per capita growth rate is going to be linear. So we have to find the slope, m, and the b value. Now that's the same as if we had to find y equals mx plus b given 2 points. We have 2 points here. But the point is in this linear function is the per capita growth rate as a function of y. Let's say here. Per capita growth rate as function of y. So that might be the little adjustment we need to make. Okay. So it's still the slope m. I might not need to call it slope, but it is the slope of this linear function. M is the change in the output function, if you will, over the change in the input, not function, output, input variable in this aspect of the function temporarily that we look at. So it's just the difference. Let's pick the first and the second point as I labeled them. So the change in the per capita growth rate is 2 minus 3 over the change in y that corresponds to that 9,000 minus 6,000, and I get negative 1 over 3,000. Then I have to put that back in. So let's maybe update. Running out of space, that's okay. Update the equation, putting in the value of m, still having to find the value of b, but I have any point that is convenient. Let's say the first one, 6,000 for y, 3 for the per capita growth rate. Plug that in, so 3 equals negative 1 over 3,000. What did we say, 3,000? No, it was 6,000, sorry. 6,000 for y corresponds to that, and that's b. So this then just simply becomes a 2, and b becomes a 5. So finally, we get our per capita growth rate as negative 1 over 3,000 y plus 5. Now, this doesn't necessarily look very appealing or familiar when it comes to our logistic equation. Our logistic model just requires a little bit of rewriting. Let me just check the question, not that we super care about it. We want to write the logistic model. All we have to do is multiply by y, both sides. dy dt is therefore, how should I write it? I'm just going to keep them like this because we want them factored anyway. But I'm going to take out 1 over 3,000 and write that in front, then have my y there, and then swap the other two around as 15,000 minus y. And there is our more familiar looking differential equation. All right, and now we can see, there's the capacity for this situation. There's my growth rate, if you want to call it that. And I think they do ask me that, what is the carrying capacity? That's right there, 15,000 for this Petri dish. Then they ask, at what, excuse me, at what population is the number of bacteria increasing most rapidly? Well, for that, I can investigate, let me move up here. I can investigate the growth rate versus the population size, because that is a parabola. So let's visualize that over here. So it's going to be y on the horizontal axis, dy dt on the vertical axis. And that's just a parabola with horizontal axis intercepts 0. And let me draw a parabola. This guy is much wider and flatter than this, but who cares? Just visualizing it. Over here is 15,000. Again, I apologize for all the knocking that you may hear, and helicopters are flying. It's craziness. I don't know what's happening. I do not know what is happening right now, but it's got nothing to do with us. So now you can see, because of the parabola, the highest growth rate is happening at this point here, which is obviously at 7,500. What is that growth rate? Well, I don't really care. It's the maximum. I can calculate it, but that's not the point. They are specifically asking, at what population do I hit that maximum? And then you can also ask, okay, well, when is that happening? Uh, Maybe I want to know when I'm going to hit this highest growth rate. But for that, we need to solve this differential equation and find the function that has time in it. So the last part of the question is, if there are initially 1,000 bacteria, how long will it take to reach 80% of the carrying capacity? And perhaps we also want to know here, this is 50% of the carrying capacity. When does that happen? But once we have the function, we can answer all the questions they want. So I originally have 1,000. I now have my initial value problem complete. And now we can go through the motions of, oops, we're out of space there. We can go through the motions of practicing to solve this differential equation. This logistic equation is a little bit more involved to solve versus your basic ones. Let me write it down again so we see it here. 1 over 3,000 y 15,000 minus y initial condition 1,000. All right, there we go. So what did we do? Well, we move all the y-related terms to the other side, separating the variables, and I'll just leave the constant with the dt side, and then we integrate both sides. But on the left, we have a partial fraction situation. Now again, we can spend an hour on partial fractions in a way that's more general than what we need. We don't need it to be a fancy topic. We just need to be able to split up this guy. And if I attempt to guess like so, an attempt at splitting this up, what do I get? Well, if I put that over my common denominator, which is the 1 I should have, showing that the split of denominators at least is correct, I would get for the first one, it's the 1, the numerator, times the opposite denominator, plus this numerator times the opposite denominator. So my y's do cancel, I get 15,000. Yet I have to get a 1. How can I manually adjust that? Well, simple enough. I just have to put a 1 over 15,000 in front, and then it'll cancel with this 15,000. Problem solved. Now, in general, partial fractions are a little bit more complicated than this, but we only need it for this specific purpose, and it's not coming up ever again. So why would I care to make things more complicated than they already are? So now you can make your life even a little bit simpler by taking this guy to the other side before I worry about the rest. So I don't want to do too many steps in one go so you don't lose track of where we are. That is not a DT. Goof. So I multiply both sides by 15,000. I might as well merge it with that guy over there. And then I get a 5. That looks a little nicer. Now I have my natural log for the antiderivative of this first 1 over y. I have my negative natural log of 15,000 minus y for this one. And I have 5t plus my integration constant. So then now things are looking a little bit more familiar. I'm going to merge these two logs with the appropriate log property, and then I can get the y fraction out of the log with by rewriting it to the exponential version of the equation. I'm going to go for a more convenient integration constant. And at this stage, it might be handy to, before I bother solving for y, use my initial value to find this integration constant. So if I plug in 1,000 for y, I have 14,000 in that denominator. That's going to be m times e to the 5 times 0, which is, of course, not 0, you goof, 1. And I get m is 1 over 14. Perhaps not the most convenient, but there it is. It tend to have some fractions, and I don't want to write them as decimals because they are non-terminating decimals. But if you want to write them in decimal form, go right ahead. Okay, so now we have to solve for y. Now, as you do more of these, it does start to fit the same logistic function formula that you could jump to. But for the first couple of examples, I want to go through the motions and see how I get to that function. And if you want to use it later on, go right ahead. But a formula too fast promotes a lack of understanding. So I multiply both sides by 15,000 minus y. Then I can multiply that in. So I have 15,000. I'm going to leave it like this. E to the 5t minus 1 over 14 e to the 5t y. And leaving it like this and not simplifying these numbers makes it easier if you ever were to derive this in general. So then I have to take the y term to the other side. That is a 14. It doesn't look like it. There we go. E to the 5ty equal to my 15,000. It's a little tedious, but in the beginning, it's good to understand how you get to that general formula. Now I can take out y, and I have 1 plus 1 over 14 e to the 5t equals, and I'm not skipping or merging too many steps so that you can follow this easily if you need to, or if you're struggling with this. Divide both sides by the bracket to get to a point where we are almost done. 1 plus 1 over 14 e to the 5t, just like the basic differential equation. For the basic exponential growth, you do this a few times. It is not super complicated. There's a lot of repetition here. So I divide throughout by this on both sides in this fraction to get 15,000 over 1 over 14 e to the negative 5t plus 1, just to make it look like the standard version of the logistic equation. And then if we were to graph this, and you can use software to graph it, do whatever you prefer. We're going to start with 1,000 here. It's going to have that basic exponential growth initially, and then the capacity is going to force it to slow down to a capacity of 15,000, which is exactly what we want. We want our function to exhibit those properties because that is in reality what is happening to the bacteria, to the population. Okay, so now let's squeeze in a page, one more, to answer those couple of questions. Now I'll just do one because they are handled in exactly the same way. Let's rewrite our function here so we can see it on the same page. It's 15,000. It is 1 over 14 e to the negative 5t plus 1. And we can double check it for sure if you're not convinced. There's our function. So we can go back here and say, and ask, oh, where did it reach the 7,500? When did it reach that maximum growth rate? You can use that, or we can stick to this question asking, how long will it take to reach 80% of the carrying capacity? So 80% of the capacity, which is 15,000. Let's calculate it so we have something to show in the chat box. But of course, you can do it in your head as well. 0.8, whoop, that's a noisy keyboard. 0.8 times 15,000, just so MathBot has something to do. Oops, not a line. And we have a target of 12,000. So that means we need to solve for t in the equation that we get when we set that equal to 12,000 for y. So we plug in everything, and t is going to be what we are looking to solve. All right, we just need to make a little correction on the ending of what we just talked about in our logistic equation. Let me just check my pen here. I'm going to blame the construction up above me, but we have this solution, this second to last step in the solution process, where I just want to clean this up, and we accidentally wrote 1 over 14 here. When we divide by 14, it's throughout. We divide by 1 over 14 e to the 5t, so it becomes in the bottom 14 e to the negative 5t when I divide by 1 over 14. So then over here, this is a 14. We're still looking for a target of 12,000, but we just used a 1 over 14 instead of a 14, which changed our answer to a weird number. It is still extremely small, but we swap it out. So this is a 14 over here. When we look for 80% of the capacity, we just plug in 12 for y, and we have our equation. Move the denominator to the top of the other side. 12,000 comes to the bottom. 15 divided by 12 is 1.25. And so we subtract 1 on both sides for 14 e to the negative 5t equal to 0.25. And so e to the 5t is then 0.25 divided by 14. So the log version of this is negative 5t equal to the natural log of that 0.25 over 14. And so we want to divide both sides by negative 5. And let's see what we get. Natural log 0.25, sorry. Natural log of 0.25 divided by 14. And we're dividing all of that by negative 5. MathBot, are you going to? I think I'll just redo it. I thought I could edit it another one. Natural log. Sometimes MathBot doesn't like me to go back and edit previously typed in stuff. Divide that by -5. MathBot says, there we go, 0.8051 days. So it does grow very quickly in that in less than a day, 0.8 of a day, the bacteria, the culture grows to 80% of its capacity. And you can also answer questions like where is the growth rate maximum? So you can plug in 7,500 in this now correct function and go through the motions of solving for t with a different target instead of 12,000. And the time frame is just really short for this one. They grow actually really fast. So hopefully that gives you a good idea of the logistic equation that you can explore further if you are more interested. Until next time.